Hi, I'm John Reese. So the Python Foundation team at Facebook essentially builds tools and integration that make Python better both inside and outside of Facebook. So for a bit of context, Facebook is now a principal sponsor of the Python Software Foundation, and Python's the third most popular language in use at Facebook. It powers many different backend services, tools, and automation systems. It's also the #1 language in use at Instagram and powers the full stack front and back. And we have multiple teams working on open source tools, including 2 core developers. And because we have so much Python code here, we need safe, reliable, and high-performance refactoring tools. So when I'm talking about refactoring, I'm generally talking about any sort of modification to the source or to the repository. Could be simple or complicated, but essentially a change to the entire repository, not just an individual file. And making one change could involve updating all the references to it. Some of the reasons we might want to do these refactorings could be enforcing consistent style or white space, could be removing ugly features like named lambdas and replacing them with real functions, or it could be changing APIs and removing redundant functions. So one of the examples start with and come back to is, let's imagine some application where it prints string literals to the user, and we'd like to go through and internationalize it so that we can print it in the user's native language. We could imagine some translation function, and we could refactor the code to look something like this. We're simply wrapping the strings with the magic function and then printing the result. And ideally, we'd also like to remove any of these to-do comments, and we want to automate this across the entire repository or code base in one fell swoop. So at Facebook, this is what we would call a code mod. We have essentially a monolithic repository where all of our projects are in a shared code base. And then this means that changing an API for a library can immediately break clients or unit tests elsewhere if you're not careful about updating all the references. Code mods essentially allow us to make these changes across the entire repository and do it simply and safely. So today I'm going to focus on automated code mods and refactoring. And one of the better ways to do this is using syntax trees. Syntax trees allow you to programmatically inspect or modify your code as if it were nested objects. And when it's done correctly, this essentially lets you guarantee that the result is syntactically valid and will compile. The most common form of syntax tree is the abstract syntax tree, or AST. This generates the standard tree leaf node form, but it's a runtime focused view of the code. It's meant for the compiler, and it might be human readable, but if we actually take our example code and use the standard AST module on it, we get something that looks kind of like this. Have a call object at the base, and that call object has attributes that point at other objects, such as the name of the function being called, or a list containing the string that we're actually giving as an argument. In Python code itself, it would look somewhat like this, same sort of structure. But this doesn't exactly look much like the actual grammar of Python, because again, this is meant to be useful for the runtime. So if we were to actually try to generate source code from this object, we would have destroyed all formatting, any comments that were in the code, and things like that. And so this is where concrete syntax trees become more useful. They're a similar concept to AST, but the point is that the tree and the objects contain everything you need in order to rebuild the original file, exactly the way it came in to begin with. This means that we can preserve white space, indentation, any comments, or even choice of quotations. And it turns out the standard library also has an implementation of this. It's called lib2to3. So this is a concrete syntax tree that was originally built for the 2-to-3 code conversion tools. Because of this, it has the benefit of being able to parse both Python 2 and Python 3 grammar. And there are alternatives to lib2to3 that you could use, like rope or baron. But the main reason that we like to use lib2 to 3 is that it means, like, because it's part of the standard library, that means that it'll be well maintained and supported going into the future. And when there are changes to the official grammar, lib2 to 3 is updated immediately. So when fstrings came out, lib2 to 3 already had support for that, and so we could potentially support it before we were actually using fstrings in production. And helpfully for us, lib2 to 3 also contains a refactoring framework. The tree structure that it generates more closely mirrors the actual CPython grammar, with leaves for the actual terminal tokens in your file, and nodes matching the grammatical elements and grouping of those leaves or other nodes. But rather than like specific classes for each individual grammar element, lib2 to 3 just uses a generic leaf and node class. It also will collapse the tree that it generates by removing any redundant elements from the hierarchy. So if we take the example from before and we parse this as Python 3 as an actual print function, we have some of the relevant grammar from CPython over here. We can expand out and figure out what the tree would actually be. So there would be a power element at the base of it that it contains the entire call as well as the previous comment. This would expand into the atom expression, and because we're not doing math, that would also contain the entire function call. And then our first real branch would be an atom, which has a name literal for the name of the function that we're actually calling. On the other end of the branch, we would have the trailer that contains the parentheses and the arguments. Inside the trailer would be the argument list. In this case, we have a single argument, which itself is a string literal token of the string that's being sent to the print function. And so we can see that there are redundant elements in this tree. The power and atom expression both represent the same elements, and atom and name also both represent the function being called. And in this case, because we're only passing one argument, arglist, argument, and the string literal are again all redundant elements. So lib2 to 3 will actually collapse this into a much simpler tree for us. So you just have the power element with branches to the name and the trailer, and inside the trailer is just the string literal. The actual objects that lib2 to 3 would generate, again, we just have two classes to worry about, leaf and base. Both of them have a type attribute, which is just an integer representing which element of the syntax or grammar it represents. The value of the leaf object is the actual on-disk representation of that token. And the prefix is just a string containing any white space, formatting, or indentation or comments that precede that element in the tree. For the nodes, we simply have a list of child elements that can contain either leaves or more nodes. So on the example, if we're just looking at the string literal, this would be represented as a leaf object. The type is string literal, and the value, again, is the on-disk representation, including the double quotes that we used. The prefix would be empty because there's nothing before it and between it and the parentheses. If we were to back out to the trailer element, we would see that that is a node object. The type is trailer, and the children is a list of the 3 leaf elements. A leaf for the left parenthesis, one for the string literal, and one for the right parenthesis. Again, the prefix is empty in this case, but if we would back out to the actual print function, you would see that the prefix would be the comment above, a new line, and any indentation. So now that we have this, how do we actually use this to build code mods? lib2 to 3's refactoring framework is built around a concept of fixers. These are classes designed for the 2 to 3 tool, where each element of the 2 to 3 conversion would have its own fixer. For instance, changing from the print statement to a print function would be an individual fixer. And the refactoring framework would then do in-place transforms to the tree using all of these fixers. So the individual fixer then has a pattern that it defines to match grammar structures in the files you're modifying. These patterns use a custom grammar, but again is a method of basically defining the collapsed grammar that you're looking for. It also allows you to nest elements and have multiple alternative options that you want to match against. And then once you have the elements you want to match, you can also capture them as well to make it easier to modify them once you found the matches. Once you have the matches, the transform method of the fixer is what actually defines how the modifications to the tree are made. They can do pretty much anything they want, add, modify, remove, or replace elements. And you can make these modifications anywhere in the tree, either above or below the element you've actually matched. So we can start building the code mod from before as an actual fixer by inheriting from the base fix class and then defining the pattern we want to search for. In this case, we're looking for power elements with the print string literal to define that we're looking for print functions, and use the trailer to say that it's like an actual function call. And note that this pattern must match, or must list every element in the match. You can't skip any nested elements, but you can use any keyword to say you want to match something regardless of what its type is. It's also possible to use asterisks or square brackets for optional elements, or the pipe to signify alternative options. And more specifically in this case, we're actually capturing the string literal here using s equals, and basically assigning that captured element to the keyword s. There are more examples of these patterns in the actual lib2to3 set of fixers. They've ranged from very simple patterns to extraordinarily complex. Then once we have the pattern set up, we can define our transform method. I'd like to first look at the actual type annotations. The node argument is either the leaf or node, depending on what your pattern has matched. And the results is a dictionary mapping those capture keywords to the leaf or node element matched by that keyword. And again, your transform method can make any modifications to the tree that it wants, but it can optionally return a new element, and the lib2to3 framework will actually replace the matched element with the one returned, which can also be a really simple way of making these changes. So if we actually want to make the change we talked about, we're wrapping the string literal in a call to translate function. It's easier to simply clone and replace the string literal. So we'll first capture it out of that results from the keyword s that we used in the pattern, and then we'll replace it with a new element that we generate. In this case, we'll be using lib2to3 helpers to actually create the appropriate elements for a new function call with the name tr, and passing the list of arguments, in this case being the clone of the string literal. We could stop here, but we want to take care of the to-do comments. So we can add a bit more to our transform by looking at the prefix values of the various nodes, and just do a simple regex substitution to get rid of any line starting with to-do I18N. In this case, we can do this straight on the node we've captured, but it's also worth noting that depending on where the comment is at, you may need to look kind of around the specifically matched element. For instance, if we had put the comment after the function call, it would actually be on the prefix of whatever element is after the function call. So now that we have this fixer class that we've built, how do we actually use it? So like I said, lib2to3 has a refactoring framework. They call them refactoring tools that will run these fixers on all the files you want to modify. And the framework will then walk the syntax tree for each file, looking for matches to the patterns listed on all the fixers. Once it finds a match, it will run the transform method of the appropriate fixer, and it'll keep track of the state of the syntax tree until all the fixers have been completed and the tree has been walked. The caveat for us is that, again, this was designed for 2-3, so by default, it look for fixers to import and use, so we need a shim in order to use custom fixers. But it's not that difficult to do. You simply override the getFixers method and essentially instantiate the fixers you care about rather than importing them. And we can actually then run all of this by instantiating our Simple refactor class, giving it the fixer we want to run, telling it to refactor some list of source files or directories. And then once it's finished, we can run summarize to get a nice output of what was changed, or depending on which tool you're inheriting from, it could also generate a nice diff output. Now, all the example code so far is on my GitHub at jreese/pycon, but this can be a lot of boilerplate, and you don't generally want to reinvent the wheel every time you do this. So this is one of the reasons why at Facebook I built a tool called Bowler. It's an open source refactoring tool, and it's released through our Facebook incubator project. Bowler builds on many of the concepts I've already presented, and it's meant to work hand in hand with lib2to3. It provides a fluent API, which allows you to chain method calls and build up the refactorings that you want to have. It's also meant to take full advantage of multiple cores and quickly and efficiently work through thousands of source files. And all this is open sourced, freely available under the MIT license. So some of the reasons for using Bowler, again, because it's based on standard library, this means it'll have day one support for new Python grammar. And more importantly, it was built to allow you to have composable functions for refactoring rather than self-contained classes. And this means you can reuse these components for future code mods and really support and productionize your refactoring systems to gain long-term residual value. And Bowler itself is designed to be used either as a standalone tool or to be integrated as a library inside of the rest of your tool chain. So the way you do refactoring in Bowler is by building a query pipeline. Bowler provides a number of selectors to generate grammar patterns to search for. It has a concept of filter functions to restrict matches to more specific conditions. And then the use of modifier functions allow you to actually make changes to the syntax tree. And Bowler then allows you to combine all of the above to generate a series of transforms. And you can end up getting the results either as unified diff, interactive output, or just writing the changes to disk immediately. So what this query pipeline looks like, if we were to implement the example from before, this is an example of the method chaining and Fluent API. So we start by instantiating the query with the files that we want to modify. We use the default selector to find a function with the name print, and this will find definition anytime the function is imported and anytime the function is called. We can then use a filter to say we only care about cases where the function is being called, and a custom filter to say we further only care about cases where the function is being called with a single string literal as the argument. We can then have a custom modifier function, very similar to what we built earlier on the fixer class, to actually make the change to the syntax tree. And once it's done, we're telling Bowler we just want to generate a unified diff. We can then run this by just saying Bowler run and the file containing this query. And we'll generate the unified diff where you see the changes to wrap the string literals in the function call and get rid of the comments. Again, we could also have this generate interactive output, so you could accept or decline each individual change, or you could have it write the changes to disk immediately. More importantly, Bowler allows you to chain multiple transforms together into one query. So let's imagine a pair of library functions. Start with anxiety, where you take a source and you just repeatedly think about it. And then you have another function called despair, where you just waste your time, because what else can you do? And maybe you have some client code that calls this with your current mood. And it's not a good mood, so let's try to fix this. We can start with a new query. Again, without any arguments, we'd query the current directory. And we'll start with a similar selector. We'll take the anxiety function. We'll use one of the default modifiers from Bowler to rename it to something more appropriate. And then we can actually modify one of the arguments in place to change its default value from 3 to 5. Once we have the full query, we can again generate the diff output and see that we've renamed the function, changed the default value, and updated the import and the place where it's called. But in this case, we're still in despair, so we can go further. We can add a new selector to the function to select despair. We can again rename it to something more appropriate. And now we can actually add an argument to it. In this case, we'll add the action we're going to take. We'll add the default value. And in this case, we'll say that it's a positional argument, so Bowler will update the caller with this argument instead of the definition. And then because this is modern Python, we can add a type annotation as well. Now we have our full query with 2 selectors, 4 modifiers, and Bowler will execute this all together and do it efficiently with 1 pass against the files. And so here we can see when we actually execute this, both definitions have been updated appropriately, and the client library has had both its imports and both of its function calls updated. But in this case, the take action function still doesn't take action. So we can build a custom modifier function to actually do something more appropriate. In this case, we'll replace the sleep call with an actual print. The simplest way in this case would be to look for the statement and replace that, but it's also possible to replace the entire function block as well. You just need to be more careful about indentation and prefixes. So we'll use one of Bowler's helpers to find the first simple statement inside the despair function. Once we've found that, we'll build a new function call using the lib2to3 helpers. And in this case, we'll give the argument as an actual F string, because again, lib2to3 uses the actual on-disk representation, so you can just write F strings as you would normally. Now we can replace the statement that we found in the function with a new simple statement node and give it the children as the actual function call. Now we can update our query once again to use this custom modifier function. And when we generate our full output, we'll see the cumulative changes for the file. So in this case, the library would have both function definitions updated, and the despair function will actually start to do something useful. In the client code, again, as before, both the imports would be updated and the function calls would be changed. And if we actually write these changes out to disk and execute it, we'll see that we think about politics and then we go vote. So this is Bowler in a nutshell. Again, like I said, it's an early access project through Facebook Incubator. The Fluent API is still kind of in works, but mostly the way I want it. But there is an incomplete set of selectors and filters and transforms, and some of the other components of Bowler are still incomplete or have rough edges. We have a high-level roadmap where we want to support more use cases. We'd like to integrate it with linter-style features and also integrate it with tools like Fabricator or other code review systems. We'd also like a more diverse base of contributors to the project and to make this a tool that's useful for everyone. So if this sounds interesting to you, please check out Bowler today at pybowler.io. We have documentation, information on how to get started with the project, how to contribute to it, and a link to the GitHub. And if you have any questions, feel free to find me in the outdoor halls or on Twitter. I'll be more than happy to answer them. And as one last reminder, please go vote. I don't want to revert this back to despair. So, thank you.
Hey, thank you, John. I have here a wonderful designed-in Petaluma Camelback water bottle for you with the North Bay Python logo.
Thank you.
Everybody, please give John Reese another round of applause.
Thank you.